Alright guys, I am back with another video, and in this video we are going to solve another challenge. So for this challenge we are going to have a linked list like this. So let me zoom in actually. So the linked list looks something like this: 1, 2, 3, 4, 5, 6. And then we will have a loop inside of this linked list. So the last node of this linked list could point to the very first node in our linked list. So like this, okay? Or it could point to the second node, or it could point to the third node, or anything else, okay? Instead of pointing to null. So it's a corrupt linked list. It's not something we would want to do on a day-to-day on our day-to-day linked list creation. And so what we essentially want to return out of our function for this example is to return the node. Let me draw this better. Is to return the node that is the head of the circular linked list. So, and by that we mean that the node that is being pointed by two pointers. So here's one pointer that is pointing to 2, and here's two pointers that is pointing to 2. So 1, 2, and then here's the node itself. Either that, or if the first node is the node that is being pointed at. Okay, so let me draw this better. So if the first node is the node that is being pointed at, okay, then that is that if the reference of the node that is given to us matches the one at the end of our circular linked list. Okay, so we could count the argument as a pointer itself, and then 2 would be this pointer here, and it would be the head of our circular linked list. Okay, so in that case, if the whole linked list is a circular thing, we would want to return the very first node that is given to us. Okay, so with those out of the way, now let's see what we can do to figure out the very first node inside of this. So let me Control Z a couple of times. Okay, so suppose this is our linked list. Now, if we traverse through this linked list, it would be like this. So we will read the value of 1, then we will read the value of 2, then 3, then 4, then 5, then 6, and then we'll come back to 2, then 2, then 3, then 4, then 5, then 6, then 2, and so on, right? So this will be the output that we get if we traverse through everything, and if we were to traverse through everything and print them out to the console. So here we can see that 2, like the linked list from 2 to 6 is repeated multiple times in our output, right? And this is the circular pattern that we are talking about. And here we can see that there is sometimes 1, or there is only once the number 1 that is pointing to 2, and other times there is the 6 that is pointing to 2. Okay, so that tells us that 2 is the head of our circular linked list. Okay, and we can see that visually, but how can we detect that programmatically? So one way would be to, I think, create a hash table of the addresses of the nodes that we traverse through. So we could basically say that we have the address of 1 and what it's pointing to. So it would be address of 2 And then we have the address of 3, address of 4, address of 5, address of 6. And as soon as we have an address that is being repeated in our hash table, we will immediately return that node or that address for that node as the head of our linked list. Okay, so this would be repeated twice as soon as we go in our first loop here, and we will return this as the head of our linked list. But this would require this would be efficient on the runtime. So this would probably be O of n. And for the runtime, if we went with the hash table method, but it would also require O of n space. So if we had a very longer linked list, that would take a lot of space from us as well. So we can do better on space side of things. So if we were to say that we had 2 pointers traversing through this linked list, so we could say that like our first pointer, that is our current node, okay, traverses through the linked list at 1 node at a time, and we have another pointer called runner that traverses through the linked list 2 nodes at a time. So this is our runner node, and this is, we will write down the values that they will grab as they traverse through the linked list. So the current node has a value of 1. The runner node has a value of 1. The current node goes to the node 2. Okay, but the runner node skips 2 and goes to 3. So 3. The current node goes from 2 to 3. The runner node instead goes to 5. The current node goes to 4. The runner node goes to, again, 2. Okay. The current node goes to 5. The runner node goes to 4. The current node goes to 6. And surprisingly, the runner node jumps to 6 as well. So they will meet at 6. And we can, we could have been comparing their values while we were traversing through while we were iterating both of these pointers. So as soon as they match, after the first match, obviously, we will remember where the match exactly happened, okay? And basically, and we can do this for a couple of other scenarios to see if we figure out any pattern. So if instead 6 was pointing to 1, so let me write down this here. So here 6 was pointing to 2, right? So what happens if 6 was pointing to 1? So let's figure that out. So this is our current node, and this will be our runner, right? So just let me speed this up and write down a couple of these scenarios, and then I'll come back and explain what the pattern is. Okay, so if you look closely, if our whole linked list is a circular has a is a circular linked list. Um, we will have this many traversals. Like the current node will traverse through the whole thing once and will end up where it started. And if our linked list is starting to have circular patterns at the next node of the first node that we passed in, uh, we will end this traversal, this normal traversal, one node before we reach the very beginning. And if we very beginning of either the circular linked list or the normal linked list that we were passed in. If we had the 3 as a node that as the head of our circular linked list, we will traverse one less time, and we will stop 2 nodes before the first node, before the we will basically traverse one less node each time that the head of our circular linked list is moved one node away from the head that we are initially passed in. All right, so that's one pattern. And what is the other thing that we can learn from this? All right, so the thing here is that if the head of our linked list is here, okay, so if the head of our linked list is here, then we will end up here, right? If both the head of our linked list that we're passing and the head of our circular linked list is the same, so like we can have the initial head and the circular head, right? If they are the same, then what happens is that we will end up, if we do this kind of thing, we will end up at the same place. So if these are the same, if the initial head, if the circular head is at 2, so it's one node away from the initial head. So if this equals one node ahead, so if circular head is one node ahead of the initial head, so if we had a loop that was like this, okay? So if we had that, then what will happen is that we will end up one node. Let me see. Yeah, we will end up one node before the circular head. So if this is the circular head, right? Or sorry, this is the circular head. So if we attach only one dot next to this 6 here, if 6 was pointing to 2, okay, if 6 was pointing to 2, we will get the circular head. And if the circular head was 2 nodes away, so let me write that down with another color. So if the circular head was instead 2 nodes away from the initial head, so 1, if the circular head was here, just like we have here, what will happen is that we will end up somewhere that is 2 nodes away from the circular head. So if we attach 2 dot next to 6, so I will attach them here first. Okay. So if I attach 2 dot next here, 1, and then 2 would be this one here, okay? If I attach 2 dot next, I will get the circular head. And same for initial head. If I attach 2 dot next here, I will get to initial head as well. And why is that happening, you might ask? Why do we get such a pattern? So the reason here is that suppose that our circular linked list here the one that we have here in red, has the length of L, okay? So it has the length of L, and we are traversing one extra node in this case from all of these L's. So when we actually traverse with the with the one node that is traversing only one node at a time, the one at the top, we are actually traversing at the speed of L, right? And then like we are traversing how many nodes that we are away from the head. So in this case 0, the circular head, and then we are traversing at normal speed. And when we increase the speed 2 times, so we skip every other node, what happens is that we are traversing that 0 node first, and then we are traversing half the nodes, right? Half the length. And then after that, what we are doing is that we are traversing another half, okay? So here you could see that we had repeated our loop 2 times. So this is 1 time, and this is 2 times. And then we arrive at where we started, okay? So if we do that, then we are doing something like this. If we are one node away from our initial, if the circular head is one node away from the initial head, then what happens is that we are doing something like this, right? And if we are 2 nodes away, just like the green case here, we are doing 2 plus L for the current node or current pointer, and 2 plus half of L and another half of L. Okay, so at any case, we are traversing through this 2 times, okay? So if I try to show you here as well, so this is related to one traversal, and this is related to another traversal, okay? So depends on it depends on what is the actual length of the linked list. So in this case, the length, so since the linked list was started at 2, the length of the linked list that was being repeated was an odd number. So that's why at one traversal we had odd numbers, and at the other we had even numbers. And that matters because we are dividing the length by an even number. So we will get all odd numbers at one traversal and one even numbers at another traversals. In other ways, an odd number is not divisible by 2, so we will get different results at each traversal, at each of the 2 traversals, because we're dividing by 2. If we were dividing the length by 3, we would get different results at each of the 3 traversals, okay? And if the length wasn't divisible by 3, that would happen. And the other thing with that is that if we had a length of 3, like if we were skipping nodes by like every 2 nodes, what would happen then was that we could have matches like add one traversal here and like 2 traversal here, but the one that would give us these same results would be at the third traversal of the runner node. Okay, so the reason we're choosing 2 is that the first traversal or the first match would automatically give us these results. Okay, because we are traversing the whole L, and the first match would always be the one that we expect it to be. But if we do it this way, even though it may seem that it would make our algorithm function faster, but in reality, what happens is that it will require us to. It will give us false positives before we reach the third traversal of the runner node. Okay, the runtime would still be almost the same, but like it is unnecessary. It will give us false positives. All right, so that's that, and you can see that the number of dot nexts here and here and like here, right, will match the number of nodes that we had before reaching to the circular head, right? So if I have 1 pointer, 2 pointer before that, or in other words, 1 node, 2 node before that, that would mean that wherever I end up at, I have to attach that many pointers to get to where the circular head is. Okay. So now with these out of the way, I think we are ready to dive into the code. And this would give us a runtime complexity of O of n and space complexity of O of 1, since we are not using that much of space. We are only using one for runner, and that is constant. It wouldn't increase by the length of our linked list. So this is for runtime and this is for space. So we can see that it's definitely an improvement in comparison with the one with the hash table. All right. So let's give it a shot then. All right. So jumping back into the code, I will try to move these from the previous example. So sorry for not doing that beforehand. So this is that. Okay. Now we have a linked list here. Let's try to make it circular. Okay, so I will remove these A and B nodes, and I will remove their print statements. I will remove these function calls. Now, here I will add another node to this linked list to make it look like the same one that we had there. So we will create a node 6, and node 6 will be a new linked list node that has the value of, I will make it 6, and it will point to node, let's say 3. And I added one extra pair of parentheses there. Okay, so 1, 2, 3, 4, 5, 6. And why am I getting this error? Node 3, we do have node 3. Okay, so node 3 is defined down there. So yeah, I will make it circular over here. So node 6.next would be node 3. Okay, so that line there would make it circular. Okay, so let's print out our, I think if we print out our linked list, we will receive an error. I don't think it will give us anything in this case. So let me try to see if that even worth the try. Yep. We don't need it to print the linked list. Okay. So it's going through a loop. Wow, computers do compute very fast. Wow, it went way too much. Yeah. Okay. So yeah, you can see what will happen if we have such a linked list. So that's why we call it a corrupt linked list. All right. So I won't print it anymore. So public static, let's call our function maybe, does it have to, yeah, it returns a node and it will call get circular head. Good. And it will receive a linked list, and I will call this one initial head. And inside here, well, we want to have a runner node, right? And I will create a current node there as well. So current node is going to be the same as initial head, and or I would argue that we can initialize it at the next node, since we don't want the first matches. So why even bother creating something like creating that match at the first place? So that's that. And another linked list node called runner node, and I will initialize it at initial head dot next dot next. Okay, so with these two lines, we are simply supposing that our linked list would always have a length of 3 at least, right? So we have to have some sort of condition or conditions at the top that filters out the linked lists that are not, like, have fewer nodes in them. So let's see. So we have dot next dot next. So if we have 2 nodes, or if we have, so if we have 2 nodes, and if they are circular, we could have that case, right? So if I say that this is the first node and this is its dot next, and the dot next of this, so let me draw it. So if this is the first node, this is the second node, and if we have a runner that is reading this like that, so this is 1, then it goes to 2, and for the other one it starts from 1, then starts and then ends up at 1, so this is a circular linked list, right? And then it goes to 1. Okay, here will be the match. Okay, so it could work at linked lists of linked 2 as well if there is any circulation pattern going on. So yeah, if there isn't any circular patterns, that means the length of the linked list could be 2. So I could say that we have a linked list node, and I will call this one circular head, and I will initialize this to be null. Okay, and I will return that circular head. And what's the issue here is always null, right? Yeah, we will fix that. All right, so we will, let's for now cover the normal cases, and then we'll come back to the edge cases. Okay, so for the normal cases, we will have while, I would say while current node is not the same as runner node. Okay, is that fair to say? Yeah, it is. Okay, since we are starting from here, we are basically skipping all of these first matches. So if that was the case, then do this loop, and at the end of each iteration, say that current node is current node dot next, and runner node is runner node dot next dot next. Okay. And what do we want to do if there is a match? So if we find that match, you're not going to the next loop, right? So we already incremented the current node and runner node, but we are not running it again, running this loop again. So we will have access to current and runner node out here, and I can basically say circular head is okay. So I need another while loop or for loop here probably. Let me see. Yeah, I will need a few conditions here to check. Five. Yeah, so after that, we need to do another check for how many nodes away from the node that we ended up. We will have a node that matches something that is that many nodes away from the initial head. So let's do that. So I will say while, so we have that current node and we have that initial head, right? So I will say while current node, and this time I will rewrite what it's inside the initial in the runner node. Okay, so current node, I will reuse that basically. Current node, while current node is not the same as initial or a runner node, okay, while they are not the same, iterate each of them. So current node dot next, sorry, current node is current node dot next, and runner node is runner node dot next. So in the code they look the same, but here the runner node is different than this runner node. I can, for the sake of simplicity and code readability, I can rename this to maybe initial head runner, and I can do that just so that it's more easily readable. Okay, so if these do match again, what will happen is that they will again be stored somewhere. Let me do this. So we will have access to this, to current node. So I will then set the circular head to be the current node. Okay. So let's run this and see if we will get the node 3 in this case, right? Which has a value of 3. So I will call this function get circular head on node 1, and I will store its results somewhere, or I will call it circular head, and I will print out the circular head data. So it will return us some address. That means we can attach it the data field. So let's run it, and we are getting 3. what happens if I change the loop, change the way the loop is? So node 2 should give us 2. Node 1 should give us 1. Node, I don't know, 5 should give us 5. And what happens if I comment out this line here? It should give us no. It isn't. Okay, so I can basically write a condition for when these null out. So it's probably the runner node. Yeah, it's runner node that is reaching null. So I could say before that, I could basically say if runner node runner node dot next was null, right? Then break, sort of. Would that help? Do I have to check 2 nodes ahead? Let me see. Okay, so yeah, we bypassed that error and we are at the next error. And this is for line 19 here. So the current node here, so if that broke, I would say we can return with the current value of circular head at this point. So we don't need to even go to this next loop to get that error. So yeah, this is now better, and so this is our error in while trying to print the data. So yeah, that works better. And so if that's the case, then we know that there's an inner loop. So then what happens if we have a linked list that has only 2 nodes in it? And the second node in this linked list is pointing to the first node. So what will we get in that situation? So yeah, we are still getting node 1, so it's working. And what happens if I remove this now? Okay. Runner node is no. Okay, so I will need to have a condition that says if runner node dot next or if runner node dot next. So if this was no, or if runner node dot next was no, then return that. So what happens if I line 12? So yeah, or if the runner node itself is no, so here we initialize it like that. Alright, so yeah. Why isn't it then throwing this error at line 10 then? Can I check it here if runner node itself was no, or that? Yeah, I'm able to do it here. So then I'll probably need to do one more check here for when the linked list has only 1 node in it, right? Because now we will get another kind of error. This one for the current node here. So I would have to say if initial head dot next was null, okay, if that was the case, so if we couldn't initialize current node, then return circular head right away. Okay, so now let's try to give it one more shot. Okay, so now we have all the edge cases covered. So if we have one node and it's not circular, it will give us that. So a node cannot refer to itself, can it? So if node 1.next was referring to itself, would it return us anything? Oh yeah, so a node can refer to itself, and it still works on that case. And so if we have one node, it will give us that. If we have two nodes that are not circular, or sorry, if it that are not circular, it would give us null if we remove that data there. Yeah, and if we have two nodes that are circular, it will give us the current head, or the correct circular head. And if we have more nodes that have a circular pattern at any point, it will give us the correct results. So we have all the edge cases covered, and this function is working as we expect it to work. So here, one more time, we have the circular head. It's initialized to null, so that if we hit an edge case and we want to return early, we return null, so that we know that there is no circular head. And if the length of the linked list is only one node, then and we can't initialize current node, and like if it was circular, then initial head dot next would have some value. But if there is only one node and it's not circular, then we will return the circular head, which is null. And then we will initialize current node and runner node, and then we will compare their values, and we will see at what point, like we will iterate them, and we will see at what point they will become equal. After they become equal, we will not loop anymore, and we will get out of the while loop, and we will store the we will have access to the value of current node that was a match here, and we will create another linked list node with the value of initial head runner, so it runs on the initial head node. And what we will do here is that we will now compare the current node that we had from the previous while loop with the initial head runner, and here we will again loop through them, but this time at the same pace, and see where the two collide. And again, we will remember the value of current node as soon as we find a match, and we will store it in circular head, and we will return it. And here we had a conditional statement that was meant to be for linked lists that are short and are not circular. So yeah, it helps us to, we are basically checking for both whether this causes any nulls, like points to any nulls, and we are also checking whether runner node is going to null out. So yeah, with that, we can wrap up this video, and I hope you like this solution, and I will see you in the next video. Bye bye.